Okay, so I think we will start since it will be a bit of a long run. We have 3 hours to go for this training webinar. I will introduce briefly myself and a bit what we are doing today. Thank you everybody for joining and welcome to today Beyonders training webinar on building the future of roads and structures. My name is Giorgia Signoretto. I'm the project officer from the European Builders Confederation, and I will open this session on behalf of the Beyonders Consortium. So today, this event brings together project partners and experts to explore how innovative worker-friendly technologies are reshaping Europe's construction sector, from road and infrastructure maintenance to building renovation and on-site safety. So as I said, we will have 3 hours and we will hear from a range of speakers representing different companies, all showcasing technologies and technology solution being developed and tested within this Beyonders project. We are particularly pleased today to have at the start of our session an intervention from the European Agency for Safety and Health at Work, which has been supporting initiative that ensure innovation goes hand in hand with worker protection. So our discussion today will cover autonomous mobile robots, aerial systems, exoskeleton, digital twins, and wearables technologies, all aim at improving safety, efficiency, and sustainability in the construction sector. Before starting, I have a few practical information for you. So this session is being recorded. So if you don't want to appear, you can turn off your camera. Please stay muted during the time. We will have a Q&A session at the end of the 3 hours run, but feel free to write down your question in the chat and we will reply to them at the end. I think we are able now to start. I will give the floor to our project leader from Acciona, Antonio Alonso Cepeda, for the introduction of the project. And I will share now my screen. 1 second. Sorry. Okay. Here it is. I hope everybody can see it. Please, Antonio, the floor is yours.
Thank you so much, Georgia. Thank you, everybody, and welcome to this event, this activity. It's a workshop that has been prepared with a lot of information, and I hope that you can enjoy these 3 hours. Well, we can start with saying that, Beyonders, this kind of acronym stands for Breakthrough European Technologies Yielding Construction Sovereignty, Diversity, and Efficiency of Resources. Basically, this project started in June 2022 and have a duration of 48 months, 4 years. And is coordinated by Acciona, and we have 21 partners with 2 affiliated companies from 9 different countries. And the idea is to start the project when we started in June with technologies at TRL 4 and to reach a TRL 6. Next, please. Well, the main objectives of Beyonders are 4 mainly, or are based in 4 pillars. To improve or increase the efficiency in process. The idea is to do the same with less energy or in a better way with with better productivity or more with more safety, but improving efficiency and efficiency in terms of energy. The second pillar is to increase the safety for workers, considering their gender and age. The project has a strong aspect, or it is very well focused on these aspects. The idea is to increase the technology sovereignty in the European Union, trying to use as much as possible technologies made here in Europe, and to generate new technologies here from in Europe. And the fourth pillar is to increase the workforce well-being. This is an important aspect for this project. As we have said, we have 21 partners. We have consultancy companies. We have the technological centers for development of robotics, digital twin developers. We have partners of communication and dissemination, experts in concrete, in 3D printing in concrete, biologists. We have managers of highways, experts in LCA and LCC, experts in wearables, exoskeletons, experts and associations in workers, experts in standardization, manufacturers of machinery in construction, experts in monitoring, and I think that, well, of course, construction companies, and of course, from Acciona, also we are a construction company that we are very interested in the development of all these technologies. The technologies that we are going to see today in this workshop are mainly three. We have focused our work in autonomous and teleoperated ground and aerial vehicles. In fact, we will see today an autonomous mobile robot for infrastructure assistance. We will see autonomous wheel loaders, and we will see drones working all together to improve the efficiency in roads. On the other hand, we will see technologies based on integrated wearable devices. For example, we will see exoskeleton and smart suits and wearable sensors working, extracting information from workers, helping them to carry out their work, and preventing some kind of accidents or damage. And finally, we will see a digital twin platform that has been developed in the project, and is the upper layer of all of technologies to manage all the information data that we are retrieving for all the technologies, to analyze everything, to give support and to manage the working of all of them. Today we are going to see two main scenarios. Two use cases based on road, because we will see road construction and road maintenance. Very different, although we have tested in the same way, in the same place, in Italy. We have carried out very different use cases, in the sense that construction and maintenance have very different necessities and problems. And you will see that with different technologies, we are able to face all of them. Technologies that have been tested have been autonomous ground and aerial vehicles, integrated wearable devices, and digital twin platform. On the other hand, we will have the building construction. It has been tested in Finland, and then we tested technologies as drones, but inside a building, flying inside a building, integrated wearable devices for workers, and the use of exoskeletons also for workers to improve the works that they do. Next.
Thank you, Antonio. So now I will stop sharing my screen and we will have the intervention from the European Agency for Safety and Health at Work by Mr. Ioannis Antifatis. I will stop sharing.
Hello, good morning from my side. I have prepared a short presentation. So if I could just share my screen. Let me know if you can see my presentation now.
It's loading. Yes, now we can see. Thank you.
Okay. Hello from my side. Good morning, everyone. My name is Yannis Anifandis, and I work as Research Project Manager at EU-OSHA, the European Agency for Occupational Safety and Health. EU-OSHA is the agency responsible for the collection, analysis, and dissemination of information relevant to occupational safety and health. We are established in Bilbao, Spain. We are one of the decentralized agencies of the European Commission, and we work in order to make European workplaces healthier, safer, and more productive for the benefit of all involved parties. In order to achieve that, we conduct a number of research projects and activities. We develop some tools like our interactive risk assessment tool. We conduct several surveys in order to identify issues that are relevant to occupational safety and health that would allow us to work and raise awareness to all the different stakeholders. We maintain NOS Wiki, where you can find a plethora of information on occupational safety and health. And also every 3 years, we run a campaign that is called Healthy Workplaces on a different topic. And the topic of this campaign, the current campaign, is on the area on digitalization, on which we have been working for the last 5 years, more or less. So based on our surveys, previous versions, but also the latest version of our SNR survey that was conducted last year, we can see that more and more enterprises today are using digital technologies, and it is only 4% of the establishments that report that are not using any digital technologies. And since we are talking about the use of technology, we can see that already in those workplaces, workers, safety officers, and the managers also discussed the impact of these digital technologies on occupational safety and health, and there is more and more concern associated with this. Because based on previous findings, we can see that the introduction of those technologies can have several effects on workers, since it is reported that the use of automations, advanced robotics that are installed currently in a number of different sectors are reported to reduce autonomy, determine the speed of work, can increase the feeling of surveillance to workers, increase workload, and by that way give rise to a number of psychosocial risks mostly. So when it comes to applications like those that are included and discussed in your project, we can see that when we are having, for example, robots interacting with workers, or when we are having wearable devices, we can see that workers report more time pressure, job insecurity, poor communication or cooperation, and long or irregular working hours as some of the potential risks. To that end, at EU-OSHA, we always support initiatives and projects like the BEEYONDERS project, since the inclusion of safety and health provisions since the design phase is the most effective approach when it comes to the protection of workers. And this project and the previous research that we have conducted present that the technology and the use of digital technologies have significant opportunities when it comes to occupational safety and health, but also when it comes to performance. But risks should effectively managed in order to protect workers as well. So based on the research that we conducted, because we identified through a foresight study 5 main areas on which we focused on our research. And these areas had to do with the automation of tasks, the use of wearable devices and smart digital monitoring systems for occupational safety and health, like wearables as you will present today in your presentations. But apart from that, smart cameras that can identify several risks. We have also focused on algorithmic management and the use of AI to manage workers, platform work, gig economy, and telework. The approach that we followed, since this was a very challenging project, I think that we started this approach and this study on the implications for occupational safety and health back in 2020, and think about how many different technologies and applications exist today that didn't exist back at that time. We thought that the best approach to follow would be to follow a task-based approach, considering that every job consists of specific tasks, and these tasks could be either physical or cognitive. So these new digital applications and AI can actually perform some tasks. And ideally, the most dirty, the most dull, and the most dangerous tasks should be performed by machines or these kind of automations, and the most creative part of the job, the most creative tasks should be performed by the workers. And in order to identify the risks and the challenges and opportunities associated with occupational safety and health, we developed this taxonomy on systems that would also allow inclusion in these of technologies that didn't exist back at that time. I think that we started the development of this taxonomy back in 2020, and applications and technologies such as generative AI and GPTs didn't exist back at that time. So the main categorization had to do with the backend, either if also the task was physical or cognitive, or a mixed task. If the task was a routine task or non-routine task, and if we were talking about assistance in decision making, for example, or full automation and substitution of the workers in performing these specific tasks. Of course, in this short presentation, I cannot go into all the details of this research because we are talking about more than 5 years of research and 5 big overview projects. However, I will just mention that when it comes to the automation of tasks area, the main sectors in which we identified, both based on the literature, but also based on the actual market in the EU, but also outside the EU, the main sectors were found to be manufacturing, transportation and storage, human health and social work activities, professional, scientific and technical activities, and construction. And some of the examples that were identified in our studies had to do with the assembly lines, with lifting of objects, autonomous guided vehicles, moving material, or autonomous cleaning and disinfection in the agricultural sector, video and image analysis program for medical diagnosis. Think about a software that could read MRA scans, for example, or X-rays, and identify areas of concern in which the physician should focus, and so on. And in order to approach our audience in an easier way, because digitalization is a topic that is not the easiest topic when it comes to occupational safety and health. We developed several case studies. In total, more than 50 case studies were developed for all these different areas that I mentioned, 16 of them when it comes to automation of tasks. And for each one of these case studies, we developed some kind of a cartoon-style representation in order to present the automation, the solution presented in the case study in an easier way. So one of the case studies which we developed had to do with some kind of a vehicular automation. Think about a software and hardware automation system that was installed into an excavator, for example, that would allow this machine, this construction equipment, to dig trenches in a kind of automated way. So the operator of the machine was not on the machine anymore. The machine could operate either in a fully autonomous mode or the human operator could still be able to supervise the process from a nearby location. Safety concerns were addressed using geofencing system, and this kind of a dull, let's say, task that could also expose the worker to things like vibrations or heat or noise could be performed easier by the automation in this machine. And for each one of the case studies, as you can see, we have developed this table presenting the main challenges for occupational safety and health, but also the opportunities. So the opportunities are those that were mentioned regarding exposure to physical risks, but on the other hand, this automation could increase cognitive demand, could also increase the fear of job loss because no operator was needed anymore in order to use these kind of machines. Issues that had to do with cybersecurity and a more broad, let's say, concern that had to do with skills, reskilling of workers, upskilling for operators, and so on. Another case study that we developed had to do with some drones inspecting work sites on gas infrastructure. So these drones were used in order to identify if there were any forgotten tools after specific maintenance procedures were performed, a task that in the past was performed by workers and was considered to be a dull task. Now it could be performed by those drones and could improve the performance of the process. In general terms, the main opportunities and challenges for occupational safety and health were categorized in three main categories, dimensions that are the physical, the psychosocial, and the organizational. In there, we identified issues that had to do with job demands. The issues of job autonomy were extensively discussed. Trust and job transformation, and specifically the impact on mental health, like stress and anxiety, when it comes to these automations and increased risk of developing this kind of psychosocial stressors, let's say, to workers. When we are talking about trust, we are talking about trust on the technology, but also the whole the different ways that the work site should be organized now, because the introduction of such intelligence machines are changing the whole way that job is performed. And it's not like a simple automating system like those introduced in workplaces in the past. And in our research, we identified the impact not only for the workplace, for the workers and the employers, but also on regards to the OSH management and the opportunities that are presented in there, but also the challenges for policy making, but also for labor inspection, because currently traditional inspection procedures are about visiting the workplace and identifying some risks, but when it comes to the use of digital technologies and especially artificial intelligence, those risks may not be that obvious for the labor inspectorates as well. And in this area, we are collaborating with the Senior Labor Inspector Committee and the Commission in order to provide material to national labor inspectorates in order to improve these procedures. When it comes to regulation, in general terms, occupational safety and health is regulated by the Framework Directive that has been transposed into national legislation into all member states. But also when it comes to automation, to artificial intelligence, to machinery and digital technologies, also some total directives and regulations like the recent machinery regulation that is replacing the machinery directive, the AI Act, but also regulations like GDPR or Data Act could complement protection of workers when it comes to the use of digital technologies. And apart from that, national legislation and policies apply in several member states, especially to those that are the most industrialized and those that are having this kind of automotive industry and are using heavy machinery compared to some others. Some of the key issues that were identified had to do with safety and accountability, transparency and human oversight, because the EU AI Act promotes this transparency and the human control by categorizing the use of artificial intelligence into four main categories. So there is this category, the lowest when technology is permitted with no specific restrictions. The yellow, let's say, transparency risk, in which the use of AI is permitted but is subject to information transparency and obligation. A high risk category in which, for example, we are talking about recruitment, medical devices. There is a conformity assessment and under specific requirements. And finally, the last category, the unacceptable risk category, in which the use of AI is prohibited, like, for example, applications for social scoring or forming public opinion, deep fake, and these kind of applications. So to conclude with the main key pointers when it comes to prevention of occupational safety and health, based on the outcomes of all the different projects on which we have been working, have to do with the prevention through design. So the earlier we consider occupational safety and health through the design and the development phase, the more effective this approach will be. A second key finding was, and these findings also come from our case studies in which we have interviewed key actors in the industry, managers, workers, safety officers, cybersecurity officers, and so on, so all involved parties. That the selection of tasks and procedures to be digitalized should be very carefully considered. So a key message was, don't automate just for the sake of automation, but automate where it makes sense to automate, and there are specific objectives when it comes to automation. That workers should maintain their job control and autonomy in order to reduce psychosocial risks, that OSH policy and OSH management system can be effective by the use of digital technologies. New tools are needed in order to conduct workplace risk assessment. At EU-OSHA, we have recently launched an OIRA, or online interactive risk assessment tool, that covers this area of automation of tasks and is based on all the findings of our previous research. Training and upskilling of workers is needed when it comes to the use of technology, and upskilling can be an opportunity but also a risk at the same time for workers. Equal access to information and transparency, and that the technology should be used for the purpose that it was intended, that workers should be consulted and participate in the implementation of these technologies. Those cases were those that were identified to be the most successful when the workers were consulted and when the tasks to be automated were also discussed with the workers. Regulation and enforcement in collaboration with the authorities and the national labor inspectorates, and exchange of expertise. And I believe that also your project, one of the values, an added value of this is that these case studies that are included would allow companies in Europe, and especially when we're talking about small and medium enterprises, to exchange experience and good practices on the use of technologies, and by that way promote a more human-centered approach in which humans will be in command instead of having only the system and the AI solution to perform the tasks. All these findings and our research is available on our website, and also in the website of our current campaign, from which you can download all the reports, case studies, policy briefs, and presentations. And that's it from my side. I try to condense all this research during the last few years in this sync presentation. I'm sure that there may be some questions, so I would be happy to respond to any question.
Thank you so much,
Back to you.
Mr. Anifantis, for your very well explained presentation. Let's see if there are any questions now for you. People can also write in the chat. We will have, as I said, at the end, the Q&A session. So we will also collect more questions there. Let's see if anyone has something to ask. I think this is good. Nobody has any question or any doubt. So thank you so much for being here and for presenting everything. And it was super interesting also to see all the case studies you are analyzing with EU-OSHA. And thank you for your support for ongoing projects as Beyonders, which of course they are linked with the with what you are doing at EU-OSHA. So thank you so much. And again, if there are any questions later on, I will pass it through you by emails.
Thank you for the invitation, and I wish you have a successful workshop.
Thank you so much. Thank you for being here.
Thank you.
So now we will go on with the rest of the training webinar. So I will share again my screen. Yes, this one. Okay, okay. Can everybody see my screen?
Yes, we can.
Okay, thank you so much. Now we have the presentation of the autonomous mobile robots for infrastructure assistant from Mr. Ivan Villaverde de la Nava from Tecnalia. Ivan, the floor is yours.
Thank you, Jordina, for the introduction. So, good morning, everyone. Well, the idea of this presentation is just to show you the whole process we have followed just to build a prototype for this specific application, starting from a very basic drive-by-wire mobile platform. So the system we have to develop have to be able to fulfill these objectives that you see here. Basically, it should be an AMR able to drive autonomously in an outdoor road environment. It should be able to measure the retroreflectivity of the horizontal signs. It should be able to have bidirectional communications with a digital twin to receive commands and to send telemetry back and the measurements from the retroreflectometer. So to achieve these objectives, we have defined a series of tasks during the project to issue the different challenges that are listed here and which are going to see during this presentation. So next slide, please. Okay. So the first thing that we need to do is to integrate into the drive-by-wire platform a set of sensors that will give it the capability to perceive its environment. So in this case, we have used a wide variety of sensors, including GPS, IMU, 2D and 3D LiDARs, optical cameras, a lot of stuff. And we have used the ROS middleware to ease the integration of the sensors, the vehicle, and all the different systems. Next slide, please. So also all the sensors and the system that they need to communicate among them and with the drive-by-wire platform. So we have equipped also in the prototype a lot of communication devices, a very extensive communication infrastructure, including scan interfaces, Ethernet, Bluetooth, Wi-Fi, and 4 and 5G wireless communications. Next slide, please. So, but the key sensor to be integrated for this application is the retroreflectometer. That it's the sensor that is actually used for measuring the reflectancy of the horizontal lines. So two aspects of the integration have to be considered. In the software side, we have developed a custom ROS driver, which allows us to control the device wirelessly through a Bluetooth connection and directly from ROS. And the hardware part, the hardware integration was a bit more tricky, mostly because of the clearance requirements of the sensor that required to be placed very close to the floor and with enough free space in front of it. So, next slide, please. So the initial designs were those you see here. Basically, they were very basic cushioned platforms in which we mounted the sensor. We discarded these early designs because we considered it was too dangerous for the sensor to be so close to the floor, only 11 millimeters at all times, while the robot was driving fast on the road. So next slide, please. So the final design you see here includes also a lifting mechanism that raises the sensor or the platform of the sensor when it's not in use, and it's directly controlled from ROS through a custom driver. This design also includes some resting wheels that guarantee not only the measurement distance from the ground, but also allows for low speed movement with the sensor deployed in case we need to make small movements to correctly place the sensor. Next slide, please. So if you remember the picture in the second slide, I think, there was not much protection from the sensor and all the equipments that I had put in the platform. So the first rainy day of testing, and we surely get a lot of those here in the Basque Country, we realized that it was not a very bright idea to have all the sensors like that. So we thought we have to install some kind of all-weather bodywork that offers some protection from at least late rain, and with enough space for all the sensors and other equipments, and with some requirements like an adequate weight-cost ratio to be easily removable, etc. So next slide, please. This design was also an iterative process. In the left, you have the first design that we rejected because it lacked inner space. And in the middle, this is the design we settled for. And so you can see we provided some space for mounting an optional lightweight robotic arm that was not required for this application because we thought it maybe will give more options for the staff. Next slide, please. So this bodywork is also complemented with several 3D printer parts that we use to protect external elements like the cameras and the mechanisms of the lifting mechanisms of the platform and so on. Next slide, please. We also considered some additional designs to protect the sensor mostly from debris and splashes, but we didn't include them in the final prototype because we don't find it really necessary, and they were putting a lot of complexity there. So next slide, please. So this is the final implementation of the bodywork as it was used in the initial field test. From this one to the final demonstrator, we made only very minor changes. Basically, we changed the position of the GPS antennas. Basically, that's it. Next slide, please. So once the AMR prototype is completed, the next step is to equip it with the required autonomous capabilities, starting by the autonomous navigation. So in this case, we wanted to test three different available approaches. The first one is the ICAS commercial solution from LSN2, LS2N. The second one is a custom 3D navigation suite that we have compiled here at Tecnalia from off-the-shelf components available in ROS. And finally, we wanted to also test a GPS-based solution for featureless scenarios where a map-based approach could be difficult to apply. Also, the three sorry, the three approaches have additional layer that translates the robot estimated position in its own framework to UTM coordinates, so it's easier to integrate it with external systems having a common framework. So now we are going to briefly review these three approaches. So next slide, please. So the ICAS solution is a commercial system based on 3D LiDAR, GPS, and inertial fusion. It uses 3D LiDAR to perceive its environment, but it flattens the 3D scans into two-dimensional maps. So this 2.5D approach is more robust for outdoor operations than purely 2D approaches, but it still doesn't take full profit from the 3D information provided by the LiDARs. So next slide, please. We also tested this full 3D navigation suite. This is a suite that it was compiled for us in Tecnalia as the result of previous EC projects. We basically integrated several independent solutions into a single, easily deployable 3D navigation suite that we have successfully used in various robots right now. It's basically based on three rather common or popular modules. So we use LeoSAM for mapping, HDL for localization, and for planning we use a combination of grid maps, estimation of the transitability, and the ROS standard navigation stack. So next slide, please. So basically what we do is we use 3D LeoSAM to create a 3D map, as the one you see here in the top left. And this map, we use it along with HDL to provide a localization within this local framework. From this 3D map, we also extract the floor as a surface that you can see there in the bottom left. And we use this surface to estimate what we call a transitability map that tries to represent the places where the robot is actually able to reach. We calculate this transitability map based on the slope and the roughness of the floor surface. So next slide, please. So for the integration of the three systems, we deployed them in a configuration that allows us to easily change between them depending on the needs. So this schema shows the architecture of how the systems has been implemented, but we are not going to go into much detail right now because we don't have much time. So next slide, please. So for the GPS and inertial fusion, we have used the robot localization module that is also a rather popular module in ROS. In this way, we are able to provide the robot pose in UTM coordinates regardless of the local world representation used for localization, whether it's 2D map, 3D map, or mapless. So next slide, please. So the second requirement was, or the second requirement for autonomous capabilities is the measurement of horizontal signs with the retroreflectometer. So this device needs to be placed very accurately over the line to be able to provide good readings. So to guarantee that, the robot should be able to detect the line and to direct itself to the correct position. So next slide, please. So for this task, we follow a visual servoing approach. We use a camera mounted coaxial to the sensor, just over the sensor in the lift tablet platform, to capture images of the line that is in front of the vehicle. The line is detected in the images, and we calculate a vector that represents the direction of the line. This vector provides the distance of the line to the center and the angle from the correct alignment. So these two values are fed to a PID controller that calculates the steering at the speed that the AMR requires to drive the sensor to the correct position. So next slide, please. So for the communications with the digital twin, we use MQTT over 4G wireless communications. We define several communications to receive commands from the digital twin and send telemetry and measurements. And locally, MQTT parser is responsible to gather information available in the different modules that are in execution in the AMR to pass this information to the digital twin, and on the other direction to capture the command messages to execute the missions composed of a series of locations that we need to measure. So next slide, please. This takes us to the final autonomous capability, which is to be able to carry out arbitrary measurement missions. So this functionality is achieved using the Tecnalia's Flexbotic Execution Manager. This is a system based on state machines that are able to execute missions or tasks defined as a sequence of skills. So the missions that we receive from the digital twin are decomposed in those skills like navigate to, detect line, deploy sensor, etc., creating a state machine-based mission that we can execute with the system. So next slide, please. So this is a quick example of one of these missions decomposed as a sequence of skills. You see it starts with a navigation skill, then it checks the result of this skill, and if it's been successful, it continues with the skill to align the sensor, and so on, so on, so on. So next slide, please. So we have made several testing rounds of the system. The testing during development was done at our facilities here in Donosti. We were pretty lucky because the parking was empty due to ongoing construction works, so we were able to use it for testing. So during these tests, we focused on testing the platform itself, the vehicle, and the different modules, but independently. So next slide, please. Yeah, so the first test that we did of field tests of the almost complete system were made in a secondary road at the town of Aladiño, close to our premises. Thanks to previous projects, we had contact with the city council, and they allowed us to temporarily cut the road for the test. In this case, we focused mainly on testing the 3D navigation suite in an outdoor environment and in the line detection and visual surveying modules. So this early test of the almost complete system allowed us to really reduce the technological risk of going directly to the final demonstrator and to identify some improvements that were implemented for the final demonstrator, like for instance the updated placement of the GPS antennas that I mentioned earlier. So next slide, and with this, I conclude my presentation. So finally, we validated the full system, including the integration with the digital twin at the use case site at the A24 highway in Italy. Here we made several rounds of type tests, like measuring the straight line, in curve, discontinuous line, also sending missions by hand, sending missions through the digital twin, etc., more or less to test the complete system. So we think the tests were very satisfactory, and we are very pleased with how the system performed. So this is all for my part. Thank you very much for your attention. If you have any question.
Thank you, Ivan, for your sorry. Okay. Thank you, Ivan, for your presentation. At the end, we will have the Q&A session, but please, if you have any questions for Ivan that you want to address to him later on, we will make sure that you will receive them also by emails. Sorry, I will share again my screen. And okay. Oops, sorry. Okay. So now we will have the autonomous wheel loader. The presenter is Mr. Mustafa Karan from Hydromec. I believe, yes. Thank you, Mustafa.
Hello.
You can start.
Okay, hello everybody. I'm Mustafa Karan. I'm in charge of the loader engineering department at Hydromec. In this presentation, I would like to introduce to our autonomous wheel loader machines, which is developed in this project BEEYONDERS. Next slide, please. For this remote and autonomous control machine, we need to develop full electronic machine, which means it is possible to control the machine by electronic signals. For conventional machines, normally we control the machine mechanical lever or hydraulic pressure. But for this case, all the machine needs to be controlled by electronic signals. Such as steering system, brake hydraulic, or implement hydraulic. Next slide, please. For this project, we used 20-ton wheel loader, which is empty weight. Bucket volume is 3.5 cubic meter. Payload is 7 ton. We used feature-proof devices like thermal cameras, 3D radars, ultrasonic sensors, GNSS antennas, and industrial computer to build the autonomous wheel loader. Next slide, please. For the building of autonomous machine, it is mandatory to communicate between industrial computer and machine own system, such as steering system or any system like brake hydraulic or implement system. So we developed algorithm and software concerning the operator's machine's conditions. Next slide, please. Could you please click the video? As you see in the video, this machine is controlled autonomously. There is no human control. Machine follow the trajectory and load the gravel. So the map of the location was created from the data recorded by drone's onboard sensors and adapted to autonomous wheel loader. And for this case, first the drone for this case, first the drone mapped the area, then sent the wheel loader. We established communication between wheel loader and drone. Next slide, please. Video. During the road construction use case, a typical and very common operation named Y-cycle was tested and validated. It is very common for this case. And we illustrate the autonomous and teleoperated functions. Next slide, please. In the Y-cycle use case or load and unload, machine needs to load the bucket fully, then needs to unload in another area or in dump truck. Next slide, please. Click the video. The other very common working condition is load and carry. Machine loads the gravel or debris from one place and carries to another place. So in this video, machine detect the obstacles in the field. Then it is possible to unload the bucket by detecting any obstacles in the field. In this test, machine traveled from point A to B autonomously and safely. It followed optimal trajectories by avoiding any obstacles, which is frequently accessed by human operators or any machines, any vehicles. Next slide, please. You see our remote control station, which is developed in this project. This remote station is for any working conditions or any remote operations. You can use this remote station in an office, and then maybe machine can be in another city, another country, or another place. 3 years ago, we showed this, or 2 years ago, I'm not sure, in an exhibition, and at that case, the machine was in Ankara, and the Opera, it's named Opera remote station, was in Spain, and we controlled the machine from Spain. It is quite compact and ergonomic. This is the new version. We have first version. This is the second version. Easy and stylish. Operator needs less effort, and then less fatigue. Possible to use from any office or any remote locations. Okay, from my side, that's all. If you have any questions, please don't hesitate to ask me.
Thank you, Mustafa, for your presentation. As I said, at the end, we will have
Of course.
the Q&A session. I will give the floor to Mr. Marco Antonio Montescrova, which will introduce us to the autonomous aerial robots.
Perfect. Thank you, Georgia. Could you hear me?
Yeah, we can hear you.
Yes.
Just a little remark, because we are a bit over time, as a bit very usual, because I know that we have a lot of information and videos. So yeah, if we can stay in the 15 minutes time, it would be great. Thank you so much.
Okay, nice. I will try to be as faster as possible. So next slide, please. Okay, so thank you everyone for attending. I'm Marco Montes from CATEC. We are a research center in Seville, Spain. And during this webinar, I will present the application of our technologies to 3 different use cases. Two of those are outdoor use cases where the drone performs some inspection, surveillance, or map creation utilities. And the other one is a indoor use case where we develop the technology to localize the drone and perform some functionalities. So I will start with the building construction case study. So next slide, please. Okay, the main goals of the aerial robot in this case study are more or less 3. The first of one, most important, is to develop the capability of fully autonomous navigate, localize itself, and avoid obstacles and so on in a safer way in those environments, because there are a very dangerous environment, will be people there. The second main utility is to create a 3D map in order to be able to analyze the progress analysis of the building itself. We deploy the technology with let's say a small example using a wall. This map we can choose if it's generated in real time. If you want, let's say, lighter and worst map, of you can post-process it and take a better map. And finally, we will produce point clouds and images to perform some safety data compliance. Here is some small workflow of this case study, and it's divided in 3 phases. The first one is the phase pre-mission. So let's say the phases before the flight of the drone. First of all, we need the BAM information. With that, we will create a point cloud to be able to localize the drone inside of the building and to know exactly in which part of the building we are walking. And after that, we or the operator, we will define the flight plan of the drone in order to ensure that the drone is getting the data that is useful and important. During the mission, we will localize the drone inside of this BAM and perform the fully autonomous operation. And finally, we will generate this point cloud and upload all the information for the digital twin. Next slide, please. This is the drone that we designed creating here in CATEC. As we will not have the GNSS information, we will localize the drone using LiDAR inertial algorithms. So that's why we have in the upper part a Oster 3D LiDAR. After that, we have the companion computer, because all the information is processed on board. In this way, the drone have the enough capability to perform by itself all the navigation. And finally, we have a payload with a thermal and visual camera in order to be able to gather thermal and visual information to perform the analysis. And the good point is that this drone is designed to the use case, and that's why it's very small and has these protections around the propellers in order to make it safer. Next slide, please. This is a small overview of the software architectures. Maybe it's too technical information, but the good point of that is that it's designed as a modular architecture in order to allow the operator to change things if it's needed. For example, if you want to change the localization algorithms, it's easy to change, or if we want to change the navigation, it's easy too. So next slide. Okay, in this slide, we are seeing the view from outside of the drone and from inside of the drone. Here is shown the LiDAR measurement real time. This orange map is the map extracted for the BAM, and as you can see, the drone is perfectly aligned and inside of this map. The blue sphere that can be seen is the trajectory defined by the operator. So for example, in this first part, it's a, let's say, easy trajectory because it's an empty space, but in the next waypoint, we have a wall in the middle, so the drone is enough intelligent to be able to detect this wall and to avoid it safely. As you will see now in these images, you are seeing the real-time image of the drone, the scans of the LiDAR, and the safe map navigation that is creating these, let's say, purple and blue colors. This is the moment where the drone have a wall in the middle of the trajectory, and in red, you will see how is the new trajectory that the drone is automatically computing to avoid the wall and to perform the safe navigation. One important and remarkable thing is that all the operative is fully autonomous from the takeoff, sorry, to the landing of the drone, and everything is computed on board. So in the case that, for example, you will lose communication with the drone will finish the inspection in a safer way. So next slide, please. This is the output of the drone. Okay, this is the map of the room where we have been walking. They are in FIRA buildings. This is an example of the post-processing map. If you want it, let's say, as lengthier and sparser, you can have it in real time. And in the right, sorry, we can see how it look like this RGB and these thermal images with the point cloud in order to perform these safety analysis and so on. Next slide. Okay, that's all for the building construction case study. Right now, I will explain the outdoors case studies. In this case study, the good point, or let's say the not easier, but the advantage that we have is that we will use GNSS localization. So we focus or reinforce in different things. In the case of road maintenance, the main objective was to be able to perform an assessment and analysis of the road and the environment of the road in real time and inside of the drone. So basically here the drone, we will have two main objectives. The first one, is to check the possible obstacles or the vegetation embedded in the road itself. And the second one is to qualitative check the state of the vertical sinks using a 3D LiDAR. Here is some workflow similar to the previous one. The first one is to define the flight plan in GeoJSON. That is basically a web page, that you can easily define waypoints to drone or to whatever. After that, configure some parameters, the speed and so on. During the mission, in real time, the drone will run deep learning algorithms and check and report the status on of the road and the signals and so on. And finally, we will upload a report to the digital twin. So next slide, please. Okay, this is a drone that we will use to this case study. It's a, let's say, Catec made drone. And the good point of this drone is that it's a very general purpose drone where you can put any kind of payloads in the bottom part. And to this case study, we decided to put a Jetson companion computer in order to perform all the computations on board. And we decided to put together a Basler camera and a bleak field solid state LiDAR. With the camera, we will be able to see the road and to perform this image analysis. And with the LiDAR that is perfectly calibrated and aligned with the camera, we will check the state of the vertical scenes. So next slide, please. As before, this is a small overview of the software architecture. We focus on the design and development of very modular software architecture in order to easily be able to change, let's say, the focus or the tasks to develop by the drone. But if it's needed, we can reuse the drone itself. So next slide, please. Okay, this is a video of the drone itself flying in L'Aquila in Italy. In the left, we can see the planned trajectory that is downloaded from the digital twin that previously the operator defined it in this GeoJSON format that I talked before. And this is an example of the drone flying over over this road. Maybe the main idea of this video is to easily understand the next ones. So please, Georgia, next slide. Okay, in this slide, we can see what the drone is seeing. In the left, we are seeing the vertical scene detection. That is the first algorithm that is running in real time. As you can see, the drone is able to detect the signal itself. And with these detections, we can check in this area how is the retroreflectivity regarding to the environment. And in the right image, we will be able to see the road in purple, and in green we are seeing the vegetation. In blue and red we are seeing obstacles. So in real time we can assess how is the real state of the road itself. Okay, next slide, please. Okay, and finally, I will talk about the rock construction use case or case study. The main goal of the drone in this case study is to create a 3D model of the environment in order to allow the other machines work and to perform some assessment as, for example, to measure the earthworks and so on. So the first part is to redefine the permission part where you can, for example, select how many overlap you want to the images for the photogrammetry, how is the flight speed, the area to cover, and blah, blah, blah. After that, during the mission, we perform a data gathering of the environment. Finally, after gather of the data in the lab, we will generate this 3D photogrammetry model and send to the digital twin to allow the other robot to work with. Next slide, please. Okay, this is the drone used. It's a commercial drone with a commercial payload. So we are using this DJI 300 30K and with the payload Temuse R1. The good point of this payload is that we are using LiDAR and RGB information. In this way, we will have the color information and the points in 3D information. So we will be able to create faster maps, faster and better maps than the, let's say, typical photogrammetry techniques. So next slide, please. Okay. I will share, or we will show an example of 3 models that we created in L'Aquila, and those are the fixed trajectories that we designed there. The good point is that you will be able to run exactly the same trajectories in different days and in different moments of the year. So this is very nice because you will be able to assess how is the progress of the rock construction by using these 3D maps. So right now I will show 3 different maps that we created in 3 different days in order to show you how is the improvement of this construction. This is an example of how looks like the photogrammetry model. Basically, that's it, I think, for the 3rd day, but with that, I would like to show you how it looks like what is more or less a photogrammetry 3D model. Okay, so next slide, please. From this map, the first day, we had this mount, the soil mount in this part of the area. So as can be seen here perfectly, this moin soil is shown in the overlapping of the map with Google Maps and in the 3D model itself. Next slide. The second day, we move this soil mound using the wheel loader to a nearer area. But it's nice because can be seen perfectly how the area where the moin soil was is flat, and now the mountain is near to that. And next slide, please. And finally, we moved it to the other side of the construction area. And the good point of this image is that we can see how the first and second places are fully empty, but now the mountain is in different location. So next slide. And this slide is only to show you a detailed screenshot of the different positions of this amount of soil during the days and how is the disposition in the 3rd day was clean for the other days areas. And I think that's my last no. And finally, this is a small overview in order to show you that the drone is not working alone, and we are integrating with this digital twin. So basically, we have 2 different ways of communication. The first one is like the real-time communication that is basic in MQTT communications, and we have another protocol in order to load the missions, load the point clouds, and so on. That is based in REST API. I think that now, yes, that's all for my side.
Thank you very much,
Thank you.
Mark Antonio, for your presentation and for being almost on time, but thank you so much. It was very interesting and we watched the video, so thank you for sharing that. And now I'm going to introduce you to our next presenter, which is Christian Di Natali from ITT. And he will present the exoskeleton and smart suits.
Hello, hi, could you hear me?
Hello, yes, we can hear you.
All right, thank you. Thank you for the introduction. Yeah, you can move on to the next slide. So today I'm going to present you these 2 devices that we call it Smart Suit and the Stream Exo. Those 2 devices are basically integrating Industry 5.0 technology such as wearable technology, Internet of Things, and artificial intelligence. I'll try to show the feature of those 2 devices in the next slide. Yeah, you can move on. I will start with the exoskeleton. You can start the video. So this exoskeleton is called the Stream Exo. It's an active back exoskeleton. So we have 2 motors on the side to support the back while doing some manual material handling activities. It's worn like a backpack, as you are seeing in the video, and it's been designed for construction workers. So we respect the requirements and the specific things that was needed to develop such a wearable technology. As you can see, there is some red strap to show where you can remove it quickly, the straps, and also we have a magnetic buckles to help the wearing phase. So we improved the design of this exoskeleton from our lab prototype in order to improve the wearing comfort and provide the high freedom of movements for the workers, in order to allow them to make a deep squat as you are seeing in the video. There is this design that also it's protected with the patent that allow one size fits all. So this allows us to wear this exoskeleton different body size and weight, which allow us to do the test in the company. You can move on to the next slide. Okay, the video, if you can start, show the main activity we have into FIRA, our partner of BEEYONDERS. FIRA is a company in Finland. We have the test organized there, where we could use this exoskeleton with 5 workers. They use it through 5 days, and we test different activities, particularly like the one you are seeing, that is the transportation of weights, load materials from a place to another one, and then we collect several data. So you can move on. It's not very good quality, this video sounds. Okay, so I'll present some results. This is based on a publication we have. It's written down there. So if you want to find more information, you can look for that. What we did in this study, this is mainly related to lab study, where we measured the muscle activity of the most important muscles related to the task, and also related to the interaction with the exoskeleton. We make some activity related to manual material handling that required dynamic lifting or static posture, and we measure the portion of assistance that required the reduction of muscle activity with the exoskeleton versus compared without the exoskeleton modality. So we usually do 2 kind of test, one with the exoskeleton, one without the exoskeleton, in order to compare the effect, and we measure the muscle activity. In the column where it's written assistance means that the task done with the exoskeleton required less amount of muscle activity respect to without the exoskeleton. So it's actually the benefit they can provide. In the middle column, there is a sort of resistance. We call it resistance. So with the exoskeleton, it might require more force provided by the user. And then the third column is the overall. So we sum the two effect. As you can see, particularly if we can go in the second table related to dynamic task, we can see that there is only one negative value related to the flexor of the leg, the rectus femoris. And this is because during a particular task that is related to the lowering the load down in a dynamic way, in order to provide 20% of assistance top of the table, it required the leg to overload a bit, which is just 1.5 points higher. So this is just to underline that we try to minimize the counter effect on other muscle and provide as much as possible a benefit on the overall muscles using this task. But of course, we need to compensate somewhere. And we decide to compensate on rectus femoris, which is the bigger muscle of the leg. So this is just a focus on this. You can go to the next one. Also, we measure the ergonomic risk reduction. This is a lab testing where we use a Kinect to measure the geometry of how the task was performed by the users. And then we make a complex task, actually 8 different tasks, where the user was moving from station on one side to the station to the other side, and lifting and lowering different loads of 5 and 10 kilograms. Next slide. We also measure the muscle activity, and you can push the right arrow to go to show the rest of the slide, please. Yeah, okay. So we measure the muscle activity of the spine, of the erector spine, and we measure that while lifting those loads, the muscle were reduced by 17%. And we make this, let's say, a study related to the equivalent weight. We introduced this approach, we call it equivalent weight. So we associate a sort of, let's say, reduction of load thanks to the exoskeleton. So what we are saying here is that when you lift the load with the exoskeleton and you are lifting, for example, 10 kilograms, these can be reduced since your muscle of the back are reduced in terms of activity. And in this case, we reduce the load of 8.2 kilograms. This is important when you calculate the ergonomic risk, which is, let's say, strongly correlated with the load lifted. So if we are able to show that the load is reduced somehow, thanks to the exoskeleton, we can associate this to the reduction of the ergonomic risk. Next slide. So this is the overall result. So at the end, what we can say that in this study, we show that the ergonomic risk was totally reduced by 34%. That was combining the effect of the muscle reduction of 17% of the previous slide, plus another 17%, I would say, due to the improvement of the ergonomy overall. So the geometry, how the user was performing the task in terms of geometry of the task. So next slide. Let's move to the smart clothing. We developed this device that we call it Smart Suit. We have 2 versions, but I mean the last version we developed and we tested into the in FIRA in Helsinki. It's the total body version that integrate 10 IMUs, so inertial measurement systems, to measure the kinematics of the whole body, and 2 EMG to measure the muscle activity of the forearm. We also have an edge computing device that acquire real-time the data from all of those sensors and run some real-time algorithm before make some data streaming on external devices. Next slide, please. Yeah. So this video show basically the test done in FIRA with the worker. So this is TRL 6, like the previous for the exoskeleton. You can see real-time reconstruction of the full kinematics of the user while moving and do whatever they are doing related with the worker and not. And yeah, you can move on. Show the next slide an application of this technology related to the analysis of next slide, please. To the analysis of the ergonomic risk. So basically, the goal here is to provide a system that can generate the risk analysis index in real time in order to evaluate and keep track of how these evolve during the day of work, during the shift. What we understood is that the workers tend to accept more risk when you get tired. So the two things are correlated. So we can track the risk and see if they are assuming wrong posture or wrong attitude while performing the activity. Next slide, please. You can start the video. So the video show this system in real time. So we are able to provide digital twin of the worker and have a trigger that as soon we lift the load, it provides a signal 1 to 0, like you see in this in blue. And this show when the load is lifted. So we can segment every task. And within this task, we can calculate the coefficient related to the ergonomic risk and associated with the geometry. You see some information related into this slide. And so we can provide a lifted index real time every time we finish one task. So we can keep track of this and provide information to the user in case it start to do wrong movement. So I think you can move to the next slide. It should be all from my side.
Yeah, I believe this is all. So thank you so much, Christian, for your presentation. Again, if we have any question, we will address them at the end, and we will make sure to send them to you by email in any case. So now we have Janne Keranen from VTT, who will present the fatigue trend analysis with the smart wearable.
Okay, thank you. Can you hear me?
Thank you. Yes, we can.
Okay, so I will shortly present you to the fatigue trend analysis, and this relates to the smart suit presentation that Christian just presented. And this fatigue trend analysis that is done by VTT, it's incorporated in the building construction use case in the BEEYONDERS, and a lot of things are happening in the building construction use case, and one of them is this using these smart wearable sensors to measure these occupational safety variables. And why are we doing this is due to the fact that a large part of injuries in the construction industry, they are due to physical strain and fatigue. And this physical fatigue is a critical challenge that workers have face everyday work. And so we figured out that if we could find a way to track and identify this fatigue, and this would enable the management of this fatigue to prevent long-term consequences. And how we are doing this, so we use these IMUs. Christian already told about these inertial measurement units, and these IMUs, they are really, really good for this real work fatigue tracking because they are cheap and they are really small. They can be easily integrated into clothing almost anywhere, and they do not interfere with the workers in their everyday work. Okay, next slide, please. And in this BEEYONDERS, we use this fatigue trend analysis in cooperation with IIT. We used data coming from this smart suit that is developed by IIT, and the data was coming from workers that performed simulated work activities at a real building construction site in Helsinki, Finland. And BEEYONDERS partner Fira provided this building construction site, and the tasks that were implemented were this hauling activity and this overhead working activity. And with this data, the fatigue trend analysis, it was able to estimate these levels of used effort throughout the work. And this is fatigue trend analysis. It can be used further analysis of different smart wearable data to predict this fatigue levels in construction site workers, and why not also in other industries. And the overall goal is to improve these workers' well-being by providing these fatigue monitoring technologies that can actually be used in a real working environment. And we have a publication coming up about this, and hopefully you can read more details about that later. Okay, that was it. Thank you.
Thank you so much, Janne, for being here and for presenting this part of the smart wearables. So again, if there are any questions, I will address them afterwards. So now I believe it's time for Mrs. Christina Nazarapis from STAM, and she will present the wearable sensors.
Yes, hello, Georgia. Thank you. And
Hello,
everyone. Okay, so in the first slide, so here I've reported the three main technologies that we have developed within Beyonders. So the first one is an indoor localization system, which provides information on the location of workers inside the building apartments, environmental monitoring stations, which measures the quality of the air, and finally, a wearable device for operator safety, which basically monitors the interaction between the workers and the autonomous vehicles. On top of this, we have developed an IoT infrastructure to ensure that the data that we register from all these technologies, we are able to transmit them to the digital twin, where they are further processed or visualized when needed. So in the next slide, we start with the indoor localization system, whose main purpose basically is to detect the time instant where specific operators enter or exit a specific apartment. In the figure on the left, this is the deployment in our lab. You can see basically that the system consists in a device which is attached to the door frame, and this device embeds a ranging sensor that we use to understand in which direction the operator is crossing the door, and a Bluetooth antenna, which is used, of course, to capture the Bluetooth signals. And then the workers on their helmet, we attach them a Bluetooth tag. This system was deployed in the building construction site, as you can see in the picture on the right. In the next slide, I have reported some picture just to see what actually is inside the system. So we have a modem, which, as I said, is used to transmit the data to the cloud. Then we have, of course, a microcontroller with the Bluetooth antenna, the ranging sensor, and then in the image on the right, you can see this custom copper shielding that we have designed. Because one of the main idea of the system is that we want to be able to filter out all those signals coming from those workers which are not crossing the door, but maybe they are just standing it in their proximity. So in the next slide, you can see some tests that we have done that just let's say, try to explain better the capabilities of the system. So in this scenario, we have two operators, operator 1, which is just standing still near the door, while operator 2, which is actually passing through the door. And in the image on the right, we have reported the signal strength of the two operators that was registered by our system. So you can see that the signal strength of operator 1 is pretty low and flat. Instead, the signal strength of operator 2, it has this curved pattern, which is due to the fact that the operator 2 is actually crossing through the door. So this means that the copper shielding that we have developed actually allow us to discriminate between an operator which is actually crossing the door and an operator which is like also maybe 1 meter far from the door, but is not actually crossing. In the next slide, instead, we have reported some tests to understand how we can understand if an operator is, let's say, going inside the apartment or going outside. This is done, as I mentioned, through the ranging sensor, which in the image that you can see, basically, this sensor projects a matrix of values, which are distances that the sensors measures in a different position. And basically, by analyzing how this distance value changes, we are able to understand in which direction the operator is crossing the door. So in this image on the right, we have reported how these distance values changes. So you can see that there is, let's say, a common pattern in how these values decrease and then increase again. So basically, by analyzing how these values decrease and increase, we are able to discriminate between an operator entering the apartment and an operator exiting the apartment. In the next slide, we move with the environmental station, which, as I mentioned, are used to give, let's say, an overall status on the quality of the air. And this is done by measuring different parameters such as temperature, humidity, particulate matter, volatile organic compounds, and NOx. And the system that we have developed is the one that you see in the pictures that were then deployed in the building construction use case. In the next slide, again, you can see a little bit from the inside what's inside the system. So we have the sensor that we use to measure all these parameters, which is the Sensirion SEN55. Then we have, again, a modem, which is used to transmit the data. The GPS, because we also want to know the exact position in which the sensor, in which the system is positioned. And then, of course, a microcontroller to, let's say, mix all the data. In the next slide, we move to the third system that I mentioned before, which is the wearable device for operator safety. As I mentioned, this device is basically used to monitor the interaction between the workers and the autonomous vehicles. If you look in the picture of the right, you can see this picture was taken in the road construction use case where we have deployed the solution. So this device consists in this, let's say, box that you see attached to the back of the worker, which contains all these sensors and hardware. And then we have this instead the GNSS antenna, which is positioned on the helmet of the worker, which is used basically to capture the signals from the satellites. So what this device, in this wearable device, we have inside an RTK receiver, which is used to, let's say, track with the precision the location of the worker. So in Beyonders, we have developed this infrastructure where basically in real time, semi-real time, we try to compute the distance between each worker and the autonomous vehicles that are on the site. And if we see that this distance falls below some predefined thresholds, we send back a signal to the worker. And thanks to this, we have a buzzer also inside the wearable device, which is activated with different intensity depending on how close the worker is to the device. And finally, we also have an accelerometer, which is used to detect possible man-down situations, so risky situation. Again, in the next slide, I have reported a little bit the inside of the device. So as I mentioned, we have the buzzer, the accelerometer, the microcontroller, the RTK board, and as for the other devices, a modem, which is used to transmit the data to the cloud. In the next slide, finally, this is the IoT infrastructure that we have developed that I mentioned before. So again, the idea is that with this technology, we're not just interested in, let's say, registering the data, but we also want to make sure that the end user can actually benefit from this data. So the data, once they arrive on the digital twin, they can be either processed or otherwise they can be visualized in a dashboard so that the managers or the end user can have, let's say, an idea on what is happening on the site. So this communication is carried out through the MQTT broker. So basically, we have some topics that we use to publish the data that we retrieved from the technologies, and then also some send back some feedback, as I mentioned before, in order to alert the workers if they are inside some, let's say, dangerous situation. And I think this was all for the wearable device. So thank you very much.
Yes, thank you so much, Christina, for your presentation. And yes, if there are any questions, we will address them at the end, or I will send them by email to you afterwards. So now we have the presentation from Jose Carlos Jimenez Fernandez from Tecnalia, who will introduce us to the digital twin using the pilot cases.
Hello, good morning. Can you hear me?
Hello. Yes, we can hear you.
Okay, thank you, Georgia, for the introduction. So I will present the digital twin that we have developed in Beyonders. So basically, the beginning point for this technology, focus on the state of the art, is that in construction, a digital model is restricted to like a static BIM model. So this is doing that we are not taking advantage of all the data that we can generate in construction operation, especially when we are talking about technology. So as, for example, the worker performance safety, as you have seen in the previous technologies that have been presented by my colleagues, environmental aspects or automated devices. So the ambition here was to implement and integrate into a common environment platform all these technologies in the construction work process that has been demonstrated in the use cases. So with this, we can provide with the full situational awareness from the state of the construction, and also provide a decision support-based system. So in the next, please. As the external layer for the more visual for the user, the end user is the interface of the digital twin. So this interface is at the top of the modular architecture that we have deployed, where you can see at the bottom, we have the data sources connected to a middleware, and this middleware will manage the data to the databases. And these databases are connected with an APIs, with an analytics and machine learning model, cloud-based, and also connected with this API to the digital twin platform interface, where we can be able to see all the data that is collected on site. So next, please. So this is the screenshot for the digital twin. We have a KPI visualization interface first to provide the user with a more friendly and clear vision on the impact of the technologies, because these KPIs have been defined against conventional baseline of the construction. No? So in here you can check what is going to be the impact of your technologies that are deployed. And we, on the other hand, we had the site operation. And for example, here you can see the digital model, and is the situational awareness part of the digital twin. No, so here in building, for example, so you can check if you have any delay on the progress, any safety issue, etc. So next, please. And this is one example of one of the services of the digital twin, that is the BIM updating service. The idea is to update the progress of the construction from the point cloud from the drones, no, that was presented before. And we have deployed an automated process to identify the built element versus the plant element, and we generate an updated BIM model with the current situation, so you are able to quickly check the construction progress inside the building from an automated data acquisition from the drones. And next, please. And on the other hand, we have the digital twin input and plus output services. The idea of these services is to compute the selected KPIs based on the data to address the well-being and safety condition of workers for health and ergonomics, planning, production control, environmental impact analysis, all the aspects that we define for the project. And as I said, this is to generate knowledge for decision makers. And in the next, please. And to finalize, these are some examples that apply to the road and the building use case. For the road, for example, the progress monitoring for the building was for the BEEYONDERS updating progress that I showed before. For the road, we deployed a model able to compare point clouds from drones, so we are able to detect the variation in earth movement for the road construction. Also, where we are using the autonomous wheel loader, we can provide with an environmental analysis because from the telemetry of the fuel consumption, for example, we can estimate the emissions, different kind of emissions, so we are able to detect if we are overpacing any dangerous value or for component. We also have a health and safety compliance checking in the building use case. That in this example, for example, you can see that it was focused on the work rights, if it's missing or not, this type of equipment. And to finalize, as we have a digital version of the reality, we have used this environment to develop training models where using virtual reality or other digital tools, we have deployed this kind of training based on real scenarios. So this approach can help to a much safer construction environment for the future. So I think it is it. This is all from my side. So thank you, everyone.
Thank you very much, Jose Carlos, for your presentation and for being here today. Again, as I said, the question will be at the end, but we'll make sure if there is any for you also to send them by email. So now we are moving to the pilot sites and testing. We already heard a bit during the technologies presentation about the pilot testing, which were done in different member states. The first one will be road construction, followed as well by road maintenance afterwards. This was done in Italy, in the highway near Gran Sasso Nord in May. And for this presentation, we have Fabrizio Federici from IceCut.
Good morning, everyone.
Hello. Okay, so I'll move to the next slide.
So the road constructions use case want to demonstrate how the integration of technologies such the autonomous vehicles, the drones, the smart vehicle, wearable, integrated in the digital twin environment can optimize the use of resources in road constructions. So, as I said, the technologies and activities involved are the drone for the photogrammetry calculation, the autonomous vehicles for the earth movements, the smart wearable RTK to tracking and for safety of the workers, and the digital twin for managing all those technologies. We can go on next slide. So we tested all those technologies in a depot area of Strade dei Parchi. Strade dei Parchi is the highway who managed the A24 highway. We tested on near the city of L'Aquila in center of Italy in a depot area, very big depot area, 8,000 square feet. The test campaign was made in May with 4 active days in which more than 20 people tested the 3 technologies, the automatic wheel loader, the drone, and the RTK. Next slide, please. So with this scenario, we want to simulate the first steps of the construction of a work zone, basically focused on the movementation of the soil of the earth. We agreed a basic workflow that is a Beyonders workflow about these technologies. Then we broke down in different tasks this workflow to be compared with the traditional activities made for the road constructions for the construction of a work zone. So the basic activities are the tracking workers' location through an heat map based on ground-based routes and activities, proximity safety checks via sound alarm with the RTK between the workers and the autonomous wheel loader, processing of the minimum and the most effective path for the automatic wheel loader, and the verification of material loading and unloading activities thanks to the photogrammetry. So, which is this basic workflow, the Beyonders basic workflow for the road construction. At the beginning of the day, the user, so the road manager, access to the digital twin interface to check the scheduled program for road construction of the day. So the digital twin activate the drone to do an initial photogrammetry of the area in which all the main places are detective, like the pile of material, the position of automatic wheel loader, the position of the workers. And thanks to this revelation and thanks to the RTK revelation for the positioning of the workers, the digital twin define the initial path for the automatic wheel loader. The automatic wheel loader communicate to digital twin that is ready to perform the activity and send the commands to the autonomous wheel loader, and the autonomous wheel loader reach the location and perform the earthwork, so loading and unloading the pile. Meanwhile, the workers can conduct their works in an adjacent area. And all the steps are repeated until the pile of material is completely moved or until the task is done. We can move on the next slide. So during all these activities, the digital twin received the information from the smart wearable, from the but also from the autonomous wheel loader. So the path is the path that the wheel loader have to do between the load and unload. It can be recalculated if needed. And at the end of, as I said, at the end of the tasks, all the tasks, the digital twin activate again the drone to make another photogrammetry of the area in which it can understand if all the work is done. The digital twin also collect this all the information of the workers and that have been captured during all the activity, and then the cycle can repeat in the other day until the work is done. So this is the basic workflow that for the road construction. We can move on. Thank you. So during the field test, we verified the capability of each technologies in the real scenario. So for the smart wearable, we recorded the data from workers' trajectory while the autonomous wheel loader was in motion. There was a trigger of alarm when workers approached too much to the autonomous wheel loader. In the calculation of the optimal trajectory for the wheel loader based on the recorded trajectory of the workers thanks to the an agent-based simulation. With the drone, we verified the photogrammetry and the comparison of the photogrammetry between the beginning and at the end of the day. And the autonomous wheel loader performed the autonomous driving following the best trajectory for work avoidance. We can move on. From an end user point of view, what changed between this approach and the conventional approach? With the conventional approach, there is a separation of the work between the workers on the ground and the wheel loader and the construction vehicles. With the BEEYONDER approach, we can somehow mix these two activities. So we have an increase of productivity thanks to the because we can mix the activities of workers on the ground and the construction vehicles. An increase of safety thanks to the RTK and the alarm that we can associate when there's an approach between the autonomous wheel loader and the RTK. And we also have an increase of the a reduction of fuel consumption. So also a reduction of CO2 thanks to the recalculation of the best path of the autonomous wheel loader. So these are the results achieved by this road construction scenario, testing the BEEYONDER technology. For what concerns the road maintenance, we made more or less the same activity with the different technologies. So the case study wants to demonstrate how the automation of maintenance and the surveillance activities, thanks to the integration of autonomous vehicles and drone together with the digital twin, can optimize the required procedures, enhance the safety, and expand the range of workers involved. We tested the drone for surveillance tasks. That means vertical check of the road signs reflectivities, but also the detections of obstacles on the carriageway. Also the autonomous inspection vehicles for the check of horizontal signs, the reflectivity of horizontal signs, and the digital twins for manage these two equipments. We can move on. We tested in those technologies in the near real fields. We tested in the same area, but in the same zone, but in different area respect the road constructions. In a paved area with the real road signs, vertical and horizontal road signs. And we tested, the test campaign was also in May and involved a lot of people. We can move on. What we can simulate, we want to simulate a new approach on the road inspection. As I said, for the road construction, we made basic workflow, a workflow for road inspections with the BEEYONDER's technologies. Then we broke down the different tasks to be somehow comparable with the current inspections procedures. So the main task were the inspections of the road marks reflectance for the using the autonomous inspection vehicle and the drone used for the road obstacle checks and the checks of the vertical signs. We can move on. So this is the basic approach, the basic workflow for the road maintenance. At the beginning of the workday or the tasks, the road manager programmed the road section to be inspected. A drone perform a flyover using the LiDAR to scan obstacles like the vegetation or the animals. The autonomous inspection vehicle conducts a retroreflectivity check on red marking and send all the results, like the drone, to the digital database. And based on the data acquired from the technologies to the digital twin, there will be an update of the maintenance status on the digital twin. So we can, with this update, we can program other interventions. We can move on. Okay, I think we jumped.
Yeah, I think this is
slide,
all, yeah.
but it doesn't matter. We can say that, that from an end user point of view, this new approach, this Beyonder approach, is quite different from the ones used in the current activities, because the current activities foresee the check of verticals. The vertical signs are has a due date, and also a certain expiring date, and also the road marks, the horizontal road marks, they have to be checked only once per year. So with this, with the Beyonders approach, we can pass from, we can say, from a schedule interval to an on-demand approach, increasing the productivities, but also increasing safety, because with this approach, the Beyonders approach, use remote technologies, autonomous technologies. So removing people from the street is always a good thing, and also use electric vehicles. So we can foresee a saving in fuel consumptions and an increase of productivities. And that's it.
Thank you, Fabrizio. Sorry for the last slide missing. I will make sure to include them at the end when we will upload all the information on Beyonders website. But thank you for the presentation and for explaining everything about the pilot sites in Italy for the road construction and road maintenance. So now we should have the building construction pilot sites, which happen in Helsinki. But I see that our presenter is still not here, because actually we are a bit ahead of time. So before we were going a bit slowly, but now we are a bit ahead. So I will just keep this for now, and we'll wait for him to connect. So I will move on the a survey that we did with Beyonders. So with Beyonders, we are also working with other European projects on the same field of construction, and we have established this cluster, which is Tech for EU construction, and here we have from Icons, we have Marco Petazzoni, who will present a survey that was delivered through the cluster. I didn't know. Yes, okay.
Yes.
Thank you, Marco.
Can you hear me? Perfect.
Yes.
So thank you very much. Good morning. So after all this presentation, we would like to share with you initiatives launched within the BEEYONDERS project. As many of you know, one of the main challenges in the construction sector is the lack of gender inclusivity. Women remain underrepresented, and too often their perspectives, their ideas are not fully integrated in the design and the impact evaluation of new technologies. So BEEYONDERS has taken these challenges seriously and is exploring the potential of emerging technologies, not only to promote innovation on technological and environmental level, but also to foster a greater gender inclusion, focusing on the experiences and the point of view of the professional figures of the sector, in order to support the adoption and the use of technologies in the construction sector. However, BEEYONDERS is not facing this challenge alone. As I mentioned before, we have launched joint initiatives with our cluster and sister project, INCUBE, Robert Arm, and the Human Tech. And for this reason, this joint initiative has been launched a survey. The survey has been designed to collect opinions from professionals, both women and men, at all levels, on how they perceive the technologies currently being developed in our project. So the goal, the aim, is to build a comprehensive understanding of the opportunities and barriers to inclusion, and to use this evidence to strengthen our future work. We are still in the response phase, so we are still collecting responses and inputs, and your support can be very helpful by participating to the survey filling. So to contribute is very simple. Just scan the QR code that you can see here in the slide on the screen and to complete the survey. It only takes 8 to 10 minutes, more or less, but it will provide us very valuable insights to make our projects more inclusive and effective. So we also kindly ask you even to share the survey within your network to your partners once we have completed. I don't have nothing to say anymore, so thank you very much.
Yes, thank you. If you can also maybe share the link on the chat, so we have it also as well there. So thank you so much for sharing this information about the cluster and this survey. And now we have the presentation of the second pilot sites, which is the building construction, and was done in Helsinki in October 2024. And I see that Tommi Pitkaranta is here from Flow Technologies, so the floor is yours.
Hello everyone, apologies for the delay from my side. One technical question, will you be sharing the slides all the time? Or...
Yes, I have it here.
Okay, good, then I'll just tell you when you're next. Good. Great, so just as background and for the start, so my name is Tommi Pitkaranta, I'm from Flow Technologies. We are a managing company for this and main beneficiary in BEEYONDERS, but we have a long history in developing lean construction methods with our group company Fira Rakennus and like affiliated entity company Fira Rakennus Oy, which is a general contracting company operating in southern Finland. And in this BEEYONDERS project, there's been mainly 3 entities from our side, which meaning that Flow Technologies is the managing company, then Decideri, which does most of the lean construction development, and then we've been using this Fira Rakennus Oy construction sites as our pilot sites for this BEEYONDERS work. So that's really the case here. But yes, as presented here, the main of the activities were done in Fira's residential construction sites. Actually, activities were done actually in 2 different sites. This presentation has one of them, but both of these sites were very similar to each other, and that's why we are able to do this generalization in that terms. As you've seen already today in these presentations, we've been testing the technology, especially done. Sorry for disturbance. Yes, so we've been testing especially the autonomous flight of drones inside the buildings for scanning the building to get the good situational awareness and use it for the management purposes. Another thing has been that we've been testing the exoskeletons, mainly for the overhead installation activity for somebody's working upright positions, but also the hauling activities at the sites. And then we've been testing the wearable sensors like smart suit to understand the muscular stress for each workers and also the environmental sensors. But yeah, more about these building sites. So there are said residential buildings. This project here had 6 to 7 floors, in total 99 apartments. We also had another project which has had 2 buildings, both of 15 floors high and 135 apartments in that project. They both use high application of prefabrication in their products. So they're mainly done from prefabricated precast concrete slabs and walls, but also the projects included, for example, prefabricated bathrooms, and part of the HVAC units has been done as prefabricated before installing them on site. Please, next slide. So about the building construction for these projects, so we were really focusing on understanding and creating the generalization of the production management methods also for these BEEYONDERS use cases, to really understand what happens at the site and what is ongoing there and how we can actually bring added value to the existing practices. And then at this slide, I'm presenting a summarized model. On the left, you can see like summarized model of weekly management. So on a weekly level, the site managers really check that what is the schedule situation, are they on track on what they're doing, and they also start planning about what type of tasks should be done during next week, and do they have the prerequisites ready. For example, is the material hauled in the installation location before somebody can start the tasks, or what they should be ordering from the logistic company and the deliveries to get all the material done. So this is what they do on weekly. And on a weekly basis, they do also these quality inspections for certain work phases that are in progress. And then, at least in Finland, we have this practice of doing a weekly safety walk in which all the things are inspected at least fully once a week. Of course, it's done every time you go to sites, but you have this dedicated safety walk for the sites. Then on daily practices, they of course tend to discuss more about what's actual ongoing work and how they can assign those things on, but also how to cope with possible changes of plan. For example, if somebody can come to work, or if there has been some accident or whatever. So that's really day-to-day and even hourly activity. And then on the bottom, we're presenting the average subcontractor or worker crew operating process. So of course, when we are starting new work phase, or new worker crew is coming to the site, first they have this what we call a kickoff meeting or implementation. So they are told the site practices and they get the induction to safety and stuff like that. But then they're usually given their first work area. After they've done this first work area, they usually do this, what we call a first run model batch or first run study. And in here we inspect that what is the quality of this working crew doing these type of tasks. And then, of course, if something is needed, it's fixed. And after this, they get more work area for themselves. So these sites included very precise, accurate management model to really check everything. And that's really where we see that the presented technology can bring a lot of benefits in the future. Next slide, please. So in practice, what we did is that in the Postiaukio site that you saw earlier, we tested the exoskeleton and wearable smart suits for the lifting and hauling, and then above head and above shoulder installation. Also for that project, we tested the drones for indoor scanning. But then actually the indoor positioning system and the sensors were tested in that another project that I mentioned. Really the key learnings from the exoskeleton and wearable smart suit is that the workers really felt that they were good for them and really helping them out. Of course, there was some initiating that they had to learn how to work with the exoskeleton, but still once they got it, they really enjoyed working with it because they felt that their everyday tasks can be done more easily using the provided technology. And then really about the drones, so this would be a huge benefit for the site management because, as said, when doing a precise construction management, there has to be a lot of inspections and checkings if everything is done, what is the quality, what is the safety. And that really means that today the site managers has to be at the site constantly or doing these checks, and most of their times are really just used for inspecting the situation rather than guiding the situation. And therefore, in case we will get this type of technology as these drones, it will be as easy as the drone could be making the flight while overnight or when people are not working. And then we will get the full situational awareness from the progress, quality, and safety, thanks to a one round instead of many different site managers doing those rounds separately and using hours of their time just by inspecting. So this would be a huge change to site management practices in case this would be applied. Then, of course, indoor positioning system provides clear benefits for especially the safety management in that sense, to really know who is on site and how can it be done, especially as we tested this in that a 15-story high building. So when you start building to high buildings, you really have to know constantly that who is inside the building during construction. For example, in case of fire, you need to know that are there workers or not to really handle the situation safety. And then indoor condition sensors, they're really good, of course, to understand the, like said, working conditions, but also especially here in Nordics, that we use a lot of concrete for the building, but then again we have a more colder and humid climate, and in that sense we need to ensure that concrete is curing properly before we install other things, and that's really beneficial to know that what are the optimal situations for the concrete to cure properly, so that we can really maximize the curing and like minimize the time need for the drying in that sense, which also leads us to better quality, but also better efficiency in the total production. Next slide, please. Yes, a bit of the results. So really, as said, there was analyzed that there's significantly smaller risk for ergonomics, the type of safety issues as we're done with the exoskeleton, because it really supports you in the correct area and helps you with the correct movement of your body. And then also with the sensors, we managed to get these values for the measured reduction in muscular stress, and then which would be then some say increase in productivity, but also increase in like what type of workers can do more variety of activities. So that's also a inclusivity ask in that sense. And then the drones, well, this is an estimate from FIRA that really if we will be getting these drones working and get those installations done, so we could save at least 3, even 8 hours per week for each site manager. So that will be meaning that, well, in average Finnish site we have 3 to 5 site managers, so it's like 1 week of work saved just by getting those inspections from those drones. And yes, as said, indoor positioning really helps you with the safety, but also with the productivity, as in more complex sites we are able to direct the workers to their actual working location, so that we can keep the like whole site managed in a proper way, but also, for example, help them with this inspecting where are my materials or where are my tools type of questions. And then yes, as said about the sensors, they really help for the safety to keep the correct working conditions, and especially avoidance of these small particles and dust, things that might cause cancer or other respiratory diseases. But yes, as in Nordics, they also really can help you reduce the actual curing time and actual total construction time for the sites. Thank you.